I'm Jeff Shapiro. I'm a professor in the Department of Electrical Engineering and Computer Science, and I'm also the director of the Research Laboratory of Electronics. My group now primarily works on things to do with quantum optics for applications in measurement and in communication. And it's led by myself and Dr. Franco Wong, who's an experimenter while I'm a theorist.
Almost in any kind of research, you need both the theory part and the experiment part. And that is true, I would say, in almost anywhere. And so the collaborations between Jeff and myself is really, really helpful. He provides the backbone of understanding theory. There are occasions in which we don't understand what we are seeing. And then he would go scribble on the board and say, aha, this is what you're supposed to see, or this is what you would be interesting to see. And then we'll go into the lab and do it.
He has some programs that are largely his own, and I have some that are mostly my own. But most of our group's efforts are joint efforts. Were he not here and no other replacement found, my group would be hobbled, because to be able to do the experimental effort and the theoretical effort together is really what has given us the great successes that we've had in recent years. Being a theorist means different things to different people. Some theorists are mathematicians who are proving deep theorems. Other people are working on algorithms. I have tended to look somewhat at the boundary between physics and system theory. And we're working on a variety of things. One of the mainstream activities is producing entanglement, producing pairs of photons that have this magic supercorrelation that quantum mechanics allows, and using that to do some elementary quantum information processing.
One of the interesting aspects of doing experiments is really to try to understand what makes it click. Quantum physics is a lot about superposition. You create two things and then you combine them, and from there you can see that it becomes entangled. So this is one of these, great things that you start from something completely classical, and by engineering it properly, you get them to be entangled for the outputs. And then you measure it, you manipulate it further to get the results that you want.
Franco is a senior research scientist, so all of his time is really devoted to research. But at a research university, postdocs and graduate students and undergraduate students engaged in research projects are learners, and somebody's got to teach them. They're not just going blind. And so Franco is teaching them a great deal. He's teaching them some of the theory related to their experiment, because to do an experiment without knowing why you're doing it, what it's supposed to accomplish, deprives you not only of understanding what your work is about, but it deprives you of saying, it didn't work this way, but I know what I'm trying to accomplish, and I believe it will work this other way.
I meet with them every week, but more importantly, I have an open door policy. So my door is open, they walk in, they have questions. As they become more senior graduate students, they would be a lot more self-sufficient. We would discuss, ideas instead of techniques or how to do this, how to do that. We discuss, gee, what can you do with your setup? Can we do these interesting experiments?
MIT and RLE, the Research Laboratory of Electronics, has the full spectrum, from people doing very fundamental things to people who are driven to solve real-world problems that may be, in fact, these days associated with medicine or biology. And there are collaborations that go on that enable these sorts of things, and it's very hard to point to any division between the two. Certainly at MIT, there's a smooth-flowing collaboration across different schools, different departments, different interdepartmental, interdisciplinary research labs. And RLE, which spans both science and engineering and couples into MIT, Harvard, Health Sciences and Technology program, is all over that map.
The RLE environment makes it so much easier to concentrate on the things that you enjoy. RLE provides a meeting place for researchers in different areas. So there are collaborations within RLE, within different areas of RLE, and that really has been very helpful.
Engineering is about problem solving. You have something you're trying to accomplish and you bring tools to bear on it. Science is about developing new and fundamental understanding. And the two at a place like MIT go hand in hand because there are things that are science now that will become engineering later. The importance of this work in a societal sense is in the future, I think, but it should not be dismissed. We live in an information age, which is all about computation and communication. And it is really enabled by quantum mechanics, although you don't usually see it as such, because the microprocessors and the semiconductor lasers that inhabit your computers and your laser comm systems for fiber communication all depend on the quantum mechanics of semiconductor band structure for their functioning. What we're talking about now in quantum information processing and communication is making quantum effects at a macroscopic level to give us these new capabilities.
I'm learning what nature is trying to give us, what nature has in store. We're specifically learning about photons, but it's really about how beautiful it is and what it can and cannot do. There are certain things nature doesn't allow us to do, and the structure is just so amazing. You can do certain things, but you can't do everything. I tell my son that, oh, I'm a great detective. I learned what nature is hiding. I try to find out what's happening and try to find solutions. It makes it enjoyable to come to work and play with things and think about new ideas and how to do this and how to do that.
As a lab director, helping the young people get going and to succeed. As a classroom instructor, seeing that light bulb go on in the students' heads. As a mentor of research students, watching them develop from someone who couldn't do very much on their own to be able to put together outstanding work that gets published and recognized and go on to their own careers. These are really wonderful things. And the other thing that I've always loved about being at a major research university is it keeps you young. Every 4 years, there's a complete turnover, more or less, in the undergraduate population, a whole new generation of very bright young people. And maybe every 6 or 7 years, a complete turnover in the graduate student population. And there are always fabulous people to talk to who are your faculty colleagues. It keeps you young, it keeps you on your toes.